Okay.
Mm, Let's start. Just wait a minute. Sharing. Sharing. Now is the screen visible?
Yes, it is visible.
Okay, okay, fine. Good evening. I am Chandrima, and this is the second week lecture tutorial session of Fundamentals of Power Electronics. Today we will be discussing about BJT, bipolar junction transistor. So if you remember, did you attend last week's lecture, last week's session?
Ah, yes.
Okay, so if you remember last week we discussed about PN junction diode, right?
Hmm.
So we discussed about the various characteristics, the static characteristics, the dynamic characteristics of PN junction diode. We also saw the power loss, different types of losses, the conduction loss and the switching losses of a BJT, a diode. So today we will be discussing the characteristics of bipolar junction transistor. Just like just as we discussed for diode, the different characteristics, power loss, etc. Similarly, we will discuss for BJT as well. These are the topics that we will cover today. First, we will cover the basic concept of BJT, how it operates and all. Then the equivalent circuit of the BJT, different modes of operation, the static characteristics and the dynamic characteristics, the power loss in a BJT, and lastly, Darlington connection. So as I was saying, last week we discussed about PN junction diode. If you remember, I discussed about two kinds of switches. One was controlled switch, another was uncontrolled switch. If I talk about uncontrolled switch, so PN junction diode is an uncontrolled switch. Why? Because there are only two terminals. One is a anode terminal, another is cathode terminal. There is no control terminal as such. So, so the diode turns on or off based on the circuit condition. We can't dictate when the diode will turn on or when the diode will turn off. But for BJT, we can dictate that. Why? Because here, if you see, we have these two terminals. Along with that, we have another terminal, a third terminal, which is the control terminal. So the presentation is visible to everyone, right?
Yes.
Okay. If any point of time, if you don't see the presentation or you can't hear me, just text or just give a okay, just text in the uh, link and let me know that you can't hear or you can't see it. Yeah, I was saying that here, if you see, we have these two terminals, power terminals. Along with that, we have another terminal. This is the control terminal that I was talking about. What this terminal do? Does the terminal we can what we can do is we can just provide. the control pulses via this terminal, and those control pulses will dictate when the BJT will turn on or when the BJT will turn off, right? So this is the one of the basic differences between diode and a BJT. The diode characteristics we all saw last day, that in the last tutorial session, that diode an ideal diode can conduct current from anode to cathode, and it can block voltage in the reverse direction. So this is the characteristics of an ideal diode. Similarly, for a BJT, the BJT can conduct current in the positive direction, and it can block only voltage in the forward direction. If you see these characteristics here, for diode, the this voltage, this locus was negative x-axis, but for BJT this locus is positive x-axis, meaning BJT can block voltage in the forward direction, and it can carry current in the forward direction as well, in the positive direction. If we just name the terminals, suppose if we just name the terminals, usually what we call this terminal, we call a collector terminal. This we call collectors, C. And this terminal we call emitter. So these two are the power terminals. And this control terminal is called base, P. So this base, via this base terminal, we can control the turn on and turn off of BJT. Is this fine till this point? Do you have a question?
No, actually, that was accidentally. I
Oh, okay.
accidentally raised that.
Okay, 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 okay. So let's proceed to the next slide. Yeah. This is the symbol of a BJT, bipolar junction transistor. We shall see why this is bipolar, why this is why this is called bipolar. So there are, I have shown two symbols. First one is an NPN transistor. So this kind of symbol where this arrow is kind of pointing at outside in the emitter, this is called an NPN transistor. Another one is PNP transistor. So here you see emitter is above, collector is in the bottom, base is same only. These two kind of transistors are there. And yeah, if you see the if you see the current directions, so from usually we talk about NPN transistors. From now on, whatever problem we will solve, whatever discussion we will do, that will be for NPN transistor. But the similar, all the things are applicable for PNP transistor as well. Okay. So base current goes like this. We inject some current through this base terminal, and if we inject the current through the base terminal, this bipolar junction diode starts conducting. There are various modes of conduction. We will see what are the various modes of operation for a BJT. But the basic principle is whenever we inject some current through the base terminal, the BJT will turn on. And if we withdraw this pulse, then BJT will turn off. The current flows like this. In this direction, the current flows. For PNP, so the arrow is already in this direction, so you can understand the current direction will be like this from emitter, and current will go like this and this. At each point of time, here the current direction is like this. At each point of time, the emitter current is the summation of collector current and base current. If you apply KCL, Kirchhoff's current law, at this node, you will see that emitter current is always summation of collector current and base current. Here also and here also. Here also you see emitter current is coming and it is getting divided into two parts. One through the base, another through the collector. So at each point of time, this relation is valid. Emitter current is summation of collector current and base current in all modes of operation and everywhere. Is it understood? Okay, so and I have written here that BJT is a current control device. Why? Why current control device? Because we are injecting a current through base, right? So as we are injecting a current through base terminal, then only this BJT starts conducting. And this current that flows through this channel, this collector current, this current is dependent on this base current, right? Based on how much current we are injecting through base terminal, the collector current will vary. So that's why we say that BJT is a current control device. Controlling this BJT current, we can control the collector current. That's why it is said. And another feature of BJT is that it has negative temperature coefficient. What does it mean? What do we mean by negative temperature coefficient? So last day we talked about power loss. There you saw that whenever a device conducts or whenever a device transitions from turn off to turn on condition or vice versa, some losses occur. So due to these losses, the temperature of the device rises. Now, negative temperature coefficient means that as the temperature of a device rises, the resistances associated with this device, it will reduce. Positive temperature coefficient means as temperature rises, the resistance will also rise. But negative temperature coefficient means that as the temperature of this device rises, the resistance will go down. So the device will try to draw more and more current because as the resistance of this channel reduces, so it will draw more and more current for the same source, from the same source, right? Even though you have not changed the source voltage, it will try to draw more current because its resistance has reduced. Is this point clear? What we mean by negative temperature coefficient, is this point clear? Okay, let's proceed to the next point. Here we have shown the equivalent circuit of a BJT. As I was talking that the collector current is dependent on the base current. This collector current, this current, it is dependent on the base current. So here I have it is drawn one dependent current source. This is the symbol of a dependent current source, meaning this is not independent. This current source is dependent on another value, another variable. Here that variable is IB. IB is base current. This is IB. This is IB. Okay. So beta IB. There is this factor beta, that is the current gain of this transistor. We shall see in later slides what is beta and how it varies with the load current and all. But for now you understand that beta is a parameter that dictates what will be the current gain of the transistor. If I am suppose giving I am injecting a current of 1 milliampere through the base, 1 milliampere. And if my beta is 100, so in the linear region of operation, my collector current will be beta times IB. That is 100 times, that will be 100 milliampere. So that is the relation. Here IB is coming, and here the emitter current is going out. So here, as I have as it is written, that emitter current is summation of I base and I collector. Another thing to note here is there is a, you can see there is a diode. A diode is drawn here. Why there is a diode? Because this is a NPN transistor. So NPN. So this is here there is a PN junction. Here there is a PN junction. And how we represent a PN junction? Simply a diode that we already saw last in the last session, that we already talked about PN junction. So this we represent, model it as a diode because it is a NPN transistor. Between base and emitter there is a diode like this. We will model it as a diode only, and there will be a forward voltage drop of typically zero point 0.7 or zero point 0.6 volt as usually occurs for a diode. So all the properties of a diode will be applicable here for this junction, B and E junction, base emitter junction, right? Okay, till this point. Okay. Now we shall see the modes of operation. This is a typical circuit of a BJT. Here there is a source voltage VCC, which we have assumed 10 volt. There is a resistance RC that we have connected externally, which suppose has a value of 50 ohm. This is the BJT, and here it is ground, and we are injecting a current of 1 milliampere through the base. So if we apply KVL here to find out what will be the collector current, the collector current is nothing but VCC, this voltage, minus VCE. VCE is the drop across this BJT. Ideally, there shouldn't be any drop, but actually there will be some drop. So this voltage is VCE. VCE. Right. So VCC minus VCE divided by RC, this resistance. Uh, So there are three modes of operation for a BJT: cutoff, linear active region, cutoff region, and saturation region that we will see later. But I already mentioned that in linear mode of operation, that here the collector current is dependent on IB like this through a factor beta. Beta is also called HFE. Okay. If you see the data sheet of a BJT, you will see in some places instead of beta, you will see this parameter HFE. So they are basically the same. Uh, okay. So yeah, if we do some calculations, so assuming beta is 100, so we can see I collector is 100 milliampere. And again, here we have written the KVL. So VC comes out to be 5 volt. From this relation only, if we just put the value of IC as 100 milliampere, RC we already know 50 ohm, VCC we know 10 volt. From here, if we find out VC, that comes out to be 5 volt. So here the P loss, we know whenever there is an overlap of V and I, there will be some loss, right? So here the loss is VC times IC. That is 5 volt we all calculated, and IC is 100 milliampere, means zero point 0.1 ampere. 100 milliampere is equal to zero point 0.1 ampere. So the loss is 0.5 watt. So the loss is not zero here. There is some loss, right? And this loss occurs in the linear region or active region. Linear region is also called the active region of operation. But when we want to use the BJT as a switch, it will turn on and turn off. There we don't use this linear region. This linear region of operation is used when BJT, we want to use the BJT as an amplifier, right? In analog, I don't know whether you have studied. In analog electronics, you will see amplifiers. So BJT can be used as amplifier in this linear region. And if we want to use it as switch, then we have to operate it in saturation region. That we will see what is the saturation region, right? So, is there any question till now? You understood, right? What I told till this point. If you don't understand any point or there is any confusion, please raise. Okay, raise a question. I don't know whether you were understanding. Um, no. So this is the linear region. Now, I what I mentioned earlier, that we need to operate in saturation mode, because in saturation mode we can operate the BJT as a switch. Switch means whether it will either be in turn like on condition or it will be in off condition. When we want to when we want to complete the circuit, it should be in turn, it should be on condition. And when we want that no current should flow, then we want it in off condition, just like a switch. So in whenever we want to use the BJT as switch, there the mode should be saturation mode, not linear mode. Please understand this. When we want to operate it as switch, ideally there should be no voltage drop across the BJT, because we already saw that for an ideal switch, there shouldn't be any voltage drop when the device is in on condition. So in ideally in on condition, VC should be 0, right? So IC, ideally IC would be zero point 0.2 ampere. If we assume the same parameters, RC is 50 ohm, VCC is 10 volt, and ideally VC is 0 volt. The drop across this BJT is 0. Then my IC would be zero point 0.2 ampere. And the condition for saturation region is your base current should be greater than IC by beta. So in linear region, we saw that IC is basically beta times IB, right? But for saturation region, your IC should be less than IB beta times IB, or IB should be greater than IC by beta. That is the condition for saturation mode. This mode is important for us because in this mode only we will operate the BJT when we will be using it in a converter as a switch. Now we shall see the static characteristics of BJT, bipolar junction transistor. Yeah, I forgot to mention why we call this bipolar, because for a BJT, both holes and electrons act as carriers. So electrons are also present and holes are also present. That's why we call it bipolar, because they are both both polarity, the carrier polarity is consists of both holes and electrons, right? That's why it is called bipolar junction transistor. So static characteristics is basically the characteristics between, yeah, so the characteristics between this VCE, which is uh, which is basically the voltage across collector emitter, like this voltage. This VC is the voltage across the device, and in the y-axis we have the collector current. This is what we plot to get static characteristics. And there are three regions. There are three regions: cutoff region, saturation region, and active region. About active region and saturation region, we already talked about. But anyway, I will again explain here. So here, how we obtain the static characteristics. So the static characteristics is something like this. So suppose you have a source here, VC. We will vary this VC value. The source voltage value, if we vary, then the VC value will also change, right? So as we change the VC value, this VC value will also change. So this goes across this x-axis. And for a particular base current, some IC will flow through this device. So this is the characteristics. So if you see, as we vary VCE, the current first the current rises almost linearly, then there comes an E, and then it becomes almost constant. And this we have plotted for various base currents. First there is 1 milliampere. Then when base current is 2 milliampere, we have obtained the characteristics. Here the collector current is slightly higher. Again, but the character is the shape is almost similar. First it rises almost linearly, then there is a knee point, and then it becomes almost constant. So if you just keep on increasing the base current, you will get similar characteristics but with higher collector current value. So these are the characteristics. So these plots we have divided in three regions. The cutoff region is when the base current is too small. Ideally, it should be zero, or the base current, when the base current is too small, that region we call as the cutoff region, because if there is no base current, the device is off. So that's why it is called cutoff region. The device is off when there is no base current. And when the device current, the collector current in this region, if you see, the collector current is almost linear. There is a, like, it is increasing linearly with like as we are increasing VC, right? So this region we call as the saturation region. This portion of linear rise, this portion is saturation region, and this region is important when we want to operate the BJT as a switch. And in this portion where the current has become almost constant, it is almost horizontal to the x-axis. This region is the active region or linear region, where the relationship is valid, where IC is equal to beta times IB. Right. So that relation is valid in active region. So these are the different modes of operation for a BJT. For us, the cutoff region and saturation region are of importance. Cutoff region means when this device is off. In saturation region, the device will be on. So, okay, till now. Can you please respond whether I can proceed, or is there any doubt regarding this characteristics? Okay. Next, we will see the dynamic characteristics. Yeah, so another characteristics is there. The characteristics is basically IV versus VBE. VBE means the base emitter voltage, this voltage, and IB is the base current, right? So, I already told you that the base emitter junction is a PN junction. So there will be a diode here. We can model it just as a PN junction diode. And if you remember the last lecture, so there the diode current rises like this. There is an E point voltage or cut-in voltage or threshold voltage after which the diode current rises exponentially. That's what we get for IB versus VB as well. The same characteristics. Here, what is shown is that with change in VC, there is a slight change in these characteristics, but it is not very significant. But yeah, there is some change in the in this curve. But this curve basically resembles the characteristic of a PN junction diode, right? So this is another static characteristics. Yeah, so I was talking about beta, right? Beta is the current gain of the BJT. If we inject a current through base IB, then we can get a current through collector, that is beta times IB. So this is the current gain. Now, idea like you could think that okay, beta is a constant value throughout every operation. Beta should remain constant, but it is not like that. Beta actually varies with IC value, the collector current value. So as the collector current increases, yeah, so first beta starts to rise, then reaches a maxima, and then again it starts to fall. So this is the characteristic. But again, the beta value changes with temperature. So this is suppose at minus 25 degree. This is T1. Then at T2, it has a higher value, and this is at a even higher temperature T3. So here the beta value is even higher. So this characteristic shifts upwards as the temperature increases. So this is beta versus IC. Next up we have, yes. So if you remember for diode we talked about the peak inverse voltage and a leakage current as well. In the reverse bias, when a diode is reverse biased, for a practical diode, some leakage current flows in the negative direction, that is from cathode to anode. And if we just exceed the peak inverse voltage rating of the diode will break down. The diode will no longer function, it will get damaged. That is the peak inverse voltage of a diode. Similarly, for BJT also we have some ratings. BJT also have a breakdown voltage rating. Suppose we are not injecting any base current, IB is 0. The base terminal is open. There is no base current that is flowing through this, that there is no base current here. So ideally, there should be no collector current as well for an ideal device. But again, here some non-idealities are present. So we will see a small amount of leakage current here that is called ICEO, which is very small, and there is a breakdown voltage of a rating of the device that is called BVCEO, beyond which the device can't withstand. The device will not be able to block beyond this voltage. It will be bad. It will be damaged. So whenever you are using one device, you should always remember that the voltage you are giving, that shouldn't be that shouldn't exceed this breakdown voltage, where whatever the device is intended to block, that voltage should remain within this voltage. Yeah, so these are these two parameters, ICU and VC breakdown, that are important for our whenever we will select the device, right? Especially this breakdown voltage, because uh, you need to see whether for your application whether your voltage will be greater than this voltage, or it will be remain within this limit, so that your device will be safe. So this rating is important. Next, Next, we have the dynamic characteristics. The dynamic characteristics essentially means the voltage and current waveforms with respect to time. So here in x-axis we have time, and in y-axis we have the various voltages and the currents. Especially we what are the important voltages and currents? We saw already that VC, this is the voltage, collector emitter voltage, then the collector current, and another one is the base current, which is basically our control parameter. Like this is the parameter that helps us to control the device, right? So here again we have divided one time period in various subdivisions are there. So the first one is the off state. Off state means the cutoff region that I already showed you. In the cutoff region, so basically in the cutoff region, there is no base current. Ideally, there is no base current. So base current is zero. So no current flows through this device. But yeah, obviously, as I already mentioned, there is some small amount of leakage ICO, but this value is very small. ICO is there, and the so the this VC voltage, as the current value is very small here, VC voltage will be almost equal to VCC. Like it will be almost equal to VCC. That's what it is shown here. VC is VCC in the cutoff region. After this point, like after this till this point, this is the cutoff region. After that, we started giving some base current, right? So the base current is rising here. We are injecting some base current through this terminal. So what will happen as we started injecting some current here? So this actually this portion, this small portion, if you can see, this portion is called the delay time, because as although we are injecting some base current, till this point the current doesn't start rising, the collector current is still ICO, right, till this point. So that this time is called the delay time. So in this point the base current is starts rising, but IC is still small and VC is still equal to VCC, almost equal to VCC. So this time is called the delay time, turn on delay time. After that, the base current like stabilizes, it reaches a value, and from this point only the current starts rising, the collector current starts rising. So and this is the load component, means because this could be a resistor, but instead of a resistor this could also be inductance or capacitance. So that's why this is called a load component. It not doesn't necessarily have to be a resistor. If it is a resistor, then the current will almost rise in a linear fashion, like this dotted line, blue line. But if the load component is not resistor, it is an inductive load or a capacitive load, then we can't say like that the characteristic will be linear. There could be some overshoot or something like this, but that will not be simply a linear characteristic. For resistive load only, the characteristic will be like this. So this time period is called the rise time, because the current rises from ICO to the value, right, IC value, a substantial current. And then there is this on phase when the device is fully on and the current is stable here at this value. And this value is VCC minus VC sat by RL load. So whenever actually when the current starts rising, the voltage simultaneously falls from VCC to a VC sat. VC sat means saturation. During saturation, the drop across the device is VC sat. So the current value is like this, that we already discussed why this comes because of the KVL. If you do KVL here in the collector emitter loop, you will get this equation. And it is already mentioned that in saturation region, I beta should be greater than IC by beta. That is the condition for remaining in saturation region. right? So this is the on period when the device is fully on. And again, if you turn it off, like if you want to turn it off, then again there is a turn off delay period where VC set and current is at this value, but we are reducing the base current. So base current is reducing, and there is a negative value here. Why negative? Can any one of you tell why the base current has to go to negative, then it will have to go to zero?
To remove the stored charges.
Yeah, right. Because there is a PN junction. So as we already studied that when diode needs to turn off, before that the stored charges needs to be recovered, right? That we called as the reverse recovery. So that's why the base current goes negative and the stored charges are removed, and then the current becomes zero. So this is the delay time, this small portion where the current is still at IC and VC is still at VC saturation. Then only the voltage starts rising when the current starts reducing here. The voltage starts rising again to VCC and the current falls here, and again it becomes here ICEO and it reaches the value of VCC. So this is the full cycle of a BJT. First there is cutoff, then the off to on transition, then on, then again on to off transition. Right. So this is the dynamic characteristics. Uh, yeah. Next we have the power loss in a BJT. So power loss in a BJT, it is pretty straightforward that whenever there will be some overlap between voltage and current, there will be some power loss. And as this is not a ideal for ideal device, it should be zero, but this is not an ideal device, so definitely there will be some power loss during conduction period as well as during the transition periods from off to on as well as from on to off. Both the transitions there will be some power loss. So here actually this ICO current, I already told this current is very small. If you multiply VCC with ICO, you will get a very small value. So sometimes we may also neglect this power loss because this is very small during this cutoff period. And next again during this period also the current is ICO and the voltage is VCC, right? So again in this period also the power loss is not significant. The power loss is significant in this region because here the voltage is gradually falling from VCC to VCE to VCE sat. Almost this is also very small, and the current is rising from ICO to IC. So there is definitely some overlap between the voltage and current, right? Yeah, so there is some overlap between the voltage and current. So here the power loss will be significant. And after that, the device starts conducting. Here the voltage is VC sat and the current is IC. Again, there is some overlap. So this is the conduction loss because here the device is conducting. This we will call the conduction loss, and this portion will be the turn on loss because here the transition is from off to on. After conduction, again there is this delay period. Here again the loss is almost negligible. And again there is this overlap when the transition is from on to off. Now it is transitioning from on condition to off condition. So the opposite case we will see here, the voltage is rising and the current is falling opposite to this transition. So there is again a overlap, and we will see how we will compute the losses. So yeah, so that there is conduction loss, there is turn on loss, there is turn off loss. Is this clear? Okay. So, yeah. So these are the various types of losses. Next, we will see the Darlington connection. So Darlington connection is what? So the objective of this Darlington connection is to increase the effective beta value, the current gain, to increase the current gain of the device. How we will achieve that? We will have this kind of a connection where there is this device, the first device, and the emitter of this first device is connected to the base of a second device. You can see this is the emitter terminal, and this is connected to the base of another device, and their collector terminals are connected like this, and the emitter of the second device is like this, and there are some resistors which will which are like useful during the reverse recovery. So when the diode will flow, the reverse recovery current will flow like this. That's why these resistors are provided, right? So one second. So presentation is still visible, right?
Yes, ma'am.
A minute. Yeah. Yeah. So what I was saying that why we require this? Why do we need to increase the beta value? What is the importance? So the importance is in the linear region. Suppose we already know that your collector current, this current is beta times the base current, right? Now, if you can effectively increase the beta value, then even if you provide a very small base current, then due to the large beta value, you can get a high collector current. That is the importance. So if your base drive is very small, the source present here, the base drive that is small. Uh, Excuse me, can you please mute yourself? Kindly mute, please. Yeah, so even if you provide a very small base current, then also you can get a high collector current as the beta value is high. For a single device, this is a kind of difficult if you use a single device, because after a point you can't increase the beta value due to the constructional limitations and everything, and other like device physics. There are some reasons. So we can connect the devices like this. So suppose we provide a current IB here, right? We are providing a current IB here. So in the linear region, what will be the collector current through for this device? The collector current would be beta 2 times IB here, right? So beta 2 times IB. beta 2 times IB here, right? Now, the emitter current is the summation of IB and I collector, but you can assume the emitter current is almost equal to the collector current because IB is usually very small. So the IB current is so small that the summation of IB and this current, we can approximate it as this current only. So the base current to this device, it would again be beta 2 times IB. Beta 2 times IB. This base current would be. As the base current is like this, as the base current is beta 2 IB, then the collector current of this device will be what? If its beta value is beta 1, then this collector current would be beta 1 and times base current, which is beta 2 IB. Is this understood? How I am getting this current? Due to this connection, this kind of connection, eventually the effective beta becomes beta 1, beta 2. This is the effective beta. That's what I have written here. So if you see, there are some in the industry, some packages are available where you will you will get ready-made packages, which is a Darlington pair. So basically, you will have this terminal, and this terminal, and the effective beta would be the multiplication of the beta of this and the beta of this. So you will get a very large beta, like you can get even 1,000 or like some hundreds of times, like some 500 or 600 up to 1,000 also you can get by implementing this connection. You can get the ready-made connection like this, or you can make it in discrete fashion. Suppose you have two devices, so you can connect them like this to get a Darlington pair, right? So this is the Darlington connection. So next we will be solving problems. Okay. So I will take a few minutes of break, like 3-4 minutes. Then we will start with the problems. Okay. So Let's start again. Yeah, the presentation is visible, right?
Yes.
Okay, so let's go through the first problem. The first problem tells that NPN BJT has HFE, that is beta of 100, base resistance is given 500 ohm, load resistance RC is 30 ohm, uh, VBE is 0.6 volt. So the drop, base emitter junction drop, this drop is VBE is 0.6 volt. VBB is 5 volt. VBB is basically this source that provides the base current, that is 5 volt. Yeah, so this yeah, so basically this with the source voltage is base source is 10 volt, and the BJT carries collector current of 200 milliampere. What is the value of VCE? Sorry. Yeah, so what is the value of VCE? So this is very simple, right? You just need to apply KVL here. KVL, like all we need is KVL in this loop and this loop. So can anyone tell what should be the steps? What should be the first step to calculate VCE? Okay, let's see how we can compute VCE here. So first of all, whatever relations we talked about in the slides, that we will use here, right? Like the relation between the base current and the collector current, the base current and the emitter current, and all these relations we will use here. Yeah, so how we can calculate? First, we need to calculate the base current. Here, if you see, the collector current is given as 200 milliampere, right? So we can readily calculate the base current by IC by beta. So that will be 2 milliampere. Okay. So that is 2 milliampere. And then if we just apply KVL in this loop, this base emitter loop, what we will find? We will find VE value. So there is some base current here. So there will be some drop with across this resistor RB. The KVL will be IBRB, then VBE, as there is a drop in the base emitter junction, 0.6 volt drop, VBE plus VEE, then minus VBB, right? So VEE eventually becomes 5, this expression. You can check by yourself applying KVL in this loop. So VEE becomes uh, 3.4 volt. Okay. So yes. VB, we already got the VE value as 3.4 volt. And then if we apply KVL in this collector emitter loop, we can calculate VCE as VCC minus ICRC. We are subtracting this drop minus VEE, right? So this becomes 10. It was given that VCC value is 10 volts. So 10 minus this was 200 milliampere, and this resistance was given 30 ohm, right? So 30 ohm we have converted it to kilo ohm. That's why 0.03. And minus VE value that we already calculated as 3.4. So this comes out to be 0.6 volt. Is this okay? The steps are okay, right?
Yes, ma'am.
Okay, okay. So let's go to the next problem. The next problem is a multiple choice question. So BJT is a current control device, voltage control device, or unipolar voltage device, bipolar charge carrier device, positive temperature coefficient device, negative temperature coefficient device, all of the above or none of the above. So this I think you guys can tell which are the correct ones.
Yeah.
Yeah, first is A, obviously, because it is BJT is current control device. Then
Option D, bipolar
option
charge carrier.
D.
uh sorry uh,
Option D, bipolar charger carrier.
Option D. D for Delhi.
yeah, bipolar charge carrier device. Yeah, right. Because from the name only we can see bipolar junction transistor. So bipolar charge carrier device. So A and D. Next,
F.
F, negative temperature coefficient. That also we saw. Another thing will be another option. The correct option would be unipolar voltage device. Why unipolar voltage device? Because it can block voltage in a single polarity. It can block. It can't block voltage of both polarities. It can only block voltage in the forward direction. That's why it is a unipolar voltage device. Right. So yeah. So the correct ones are written here. Collector current is a function of base current. That's why it is a current control device. It has carriers, both the carriers, electrons and holes. So it is a bipolar charge carrier device, blocks voltage in a forward direction. So unipolar voltage device, and it has negative temperature coefficient. So A, C, D, and F are the correct options. Let's go to the next question. This is also pretty simple. Which region is characterized by the condition IB is greater than IC by beta? We already saw in the saturation region, we need to maintain this relationship. IB should be greater than IC by beta, then only the device will be in saturation region. And what is this region commonly referred to? So the correct option is 2, because and it is saturation region, right? So actually, saturation region here, I think the option is not correct, because this region is active region and this region is saturation region. So actually this linear region, they have not specifically mentioned, but like basically this region is saturation region. I already showed you guys. So if we just mark it up, so these portions are saturation region portions, this portion. And this portion where the current is kind of constant, this is the linear region. So in saturation region only this condition is valid. So that's why this region is the saturation region. And here I don't know like whether they are telling it as 1 or 2, but this region. So I think it would be 1 and saturation. This is the correct answer. Fine. Is it okay? Okay, let's go to the next question. Here what they are asking, they have given the dynamic characteristic for the given circuit is, so this is the dynamic characteristic. VC sat is given, saturation voltage drop, IC is given, ICO is given, VCC is given, this source voltage is 9 volt, rise time is this one. So this portion is the rise time, TR. This portion is TR. Rise time, fall time. This is the fall time. This portion is the fall time. And T on is given. This is the T on period from this point to this point. This is the on period when the device is on. This is 50 microsecond and the operating frequency is 10 kilohertz. So find the total power loss in the device. Right. So we already saw that power loss happens, the like major power loss happens basically during this conduction period and these two periods, the off to on transition and on to off transition. In these periods also some loss happens, but they are very small compared to these losses. So let's see. But anyway, I have calculated this losses the during the cutoff region as well. So what is the loss during this cutoff region? The loss is, first we have calculated the off time because off time was not given. So off time I have calculated from the total time period. The total time period is 1 by, so here TS is basically reciprocal of our operating frequency. Operating frequency is given as 10 kilohertz. So if we do 1 by Fs, sorry, the handwriting is like very bad here. So TS is reciprocal of Fs. So it comes out to be what? What will be the TS? If Fs is 10 kilohertz, TS should be what? 100 microsecond. Fine. My TS would be 100 microsecond. So we have TS, we have this T on. T on is given as 50 microsecond. We have TR, we have TF. So from subtracting all of this from TS, we get 35 microsecond. This is our off time, right? Yeah. So this time I am talking about. This time and this time also, like this portion also. So during the cutoff time, the power loss is VC because the voltage is VCC in this time. So 9 volt. Then ICEO, the value is already given 100 microampere, and this value we got as 35 microsecond. And then the along with that we need to multiply the frequency because this quantity is the energy, and multiplying the frequency with the energy we get the power, that is P cutoff. So you can see this is very small. This is 0.33 milliwatt. So we can ignore also this value, we can ignore also. Then we have computed the conduction loss. During the conduction loss, the voltage across the device is VC saturation. So this voltage, this blue color waveform, this is very small value, and it is given as 0.2 volt in the question. And IC value is also given as 5 ampere. So 5, then the on time 50 microsecond, and multiplied by the frequency. So at each time you need to multiply the frequency, because voltage current times this quantity is energy. From energy, if you want to get the power loss, you need to multiply it with the operating frequency. So it comes out to be 0.5 watt. So just compare this value and this value. See, this value is so small, 0.315 milliwatt, and this is 0.5 watt. So this loss is like much higher than this loss. And we have another two losses, the losses during the transitions from off to on and from on to off. These two transitions we need to calculate. So earlier I told you how we usually calculate these losses when your voltage is also varying, voltage is falling from this VCC to VCE set, and your current is rising from ICO to this IC value. So both these quantities are variables of like varying with time. So you need to have the expressions of VT and IT, and you need to integrate it over the time period, right? So if we just see the equations of the voltages and currents, suppose we want to obtain the voltage expression, right? During this period when the voltage is kind of from falling from VCC to the VCE set, right? So what will be the voltage equation? Voltage equation would be, so we can assume it as 0, or you can also assume it at VCE set. So I have assumed it as 0. If you so you can also, for accuracy, you can also exactly take VC set value. If we assume it as 0, then what will be the value? The value would be so VT would be what? VT would be uh, VCC times 1 minus TR, T by TR. Is this fine? I am talking about this portion, like this portion. This will be our voltage equation with respect to time. Similarly, we can also obtain the current equation. Current equation would be, this is rising linearly. So our IT would be IC times T by TR, right? This is okay, right? For all of you. So now we have the voltage expression as well as the current expression. We can simply put it here. If you integrate it from 0 to Ts, and like it would be obviously from 0 to TR, because the equation is valid only in this time span. So it would be 0 to TR other, and the total time period is Ts. So this comes out to be this expression. Similarly, from in this period when the device is transitioning from on to off, we can have similar, we can find out the loss similarly by integrating the voltage and current over time and again dividing it over one time period. So the expressions are this and this during on, and this is during off. Okay. So now we have all the expressions. We can simply put the values and we can obtain the loss. So here on loss comes out to be 0.375, and off loss comes out to be 0.75. So if you just add all these losses, the conduction loss and this loss, then we will have the total loss. Okay. So we will have the total loss. So P total would be P conduction plus P switching. Okay. Switching loss comprises of this turn on as well as turn off. Okay. All these two losses. That is the total switching loss. So just you can just add it. Sorry. You can just add it and you can have the total loss. Okay. Next we have this question. For transistors Q1 and Q2 shown in the figure, they are identical. Q1, Q2, these two transistors are identical. Each has DC current gain of beta, which is 100. So find out the voltage V0. This voltage you need to find out, right? So let's see how we can find out this V0. Just a minute. So yeah. So we need to find out V0, right? For finding out V0, like similar approach we can have. Like there are the all the like some two, three expressions are there, and you just need to apply KVL or KCL. Just simply like that. So how can we do that? First of all, we need to find this base current, right? Base current of this first transistor. So this is pretty straightforward. We already have V in equal to 5 volt, and the base emitter junction, this voltage is 0.7 volt, it is given, and 0.7 volt again for this transistor as well. So if we apply KVL in this loop, in the base emitter loop, what we find? We find IB1 as V in minus 0.7, again minus 0.7 by this resistor, which is 500 kilo ohm. So this comes out to be 7.2 microampere. Okay. This is the base current of this transistor, right? Now, what will be IC1? What will be the collector current of this transistor? It will be simply beta times IB1. So beta is given as 100, so 0.72 milliampere, right? So 7.2 times 100, and this is in microampere. So 100 divided by 1000. So yeah, so that would be 0.72 milliampere. What will be the emitter current? Emitter current is the summation of collector and base current. So this is 0.727 milliampere, right? And this emitter current is basically the base current of Q2. This is basically a Darlington pair, right? Here the emitter of one transistor is connected to the base of another transistor. IE1 is the base current of Q2. IE1 is 0.727 milliampere. So once we have the I base current of this transistor, again, we can find out IC2. What will be IC2? This is again beta times IB2. So beta times of this current, that is 0.100 times 0.727 milliampere. Once we have the current through this device, the collector current through this device, and the collector current of this device, the current drawn from the source is the summation of these two current, because this current is coming and it is getting divided into this current and this current. So the voltage drop here would be VCC minus IC1 plus IC2 times 100, because the summation of these two current is flowing through this resistor. That's why we need to sum these two currents and times 100. So this will be the voltage V0. This is 7.658 volt. So is this okay? Is this fine? The how I calculated V0 here?
Yes, ma'am.
Okay. So we can go to the next problem. So what they are saying, this figure shows the connection of two BJTs Q1 and Q2. Will this connection work under parallel condition and why? So there are four options. What do you think? What is the correct option? Is this connection viable? Is this connection sustainable? Can we apply this? So this here two BJTs are connected in parallel, right? The base is connect the base of this transistor is connected to the base of this transistor. So the bases are connected, the collectors are connected as well, and that emitters are also connected. So the two BJTs are in parallel. So is this connection okay, or this can't work?
Work actually.
Sorry, can you repeat?
Yeah, the option is D, I guess.
Yeah, correct option is D. Can you say why? What is the reason?
Yeah,
What
the
will happen?
effective temperature once the like if suppose like there'll be some difference even though it is shown it is kept as identical, there'll be some
Yeah,
difference. So
right.
if one yeah, so if one temperature rises, then that current rises and it becomes like a positive feedback.
Yeah, right. You are absolutely right. So, here the reason is that I have explained it in the next slide. So, BJT, we all know that BJT has negative temperature coefficient, meaning whenever the temperature of the BJT rises, the resistance falls. So now, if you see these two devices, suppose the temperature of Q1 is slightly higher than temperature of Q2, because even though these two devices are identical, we assume, but practically two devices cannot be exactly identical. Some difference will be there. So while manufacturing, you can't make two devices exactly 100% identical. There will be some very minor mismatch. So due to that, suppose Q1 temperature is slightly higher than temperature of Q2. What will happen then? The resistance of Q1 will reduce compared to resistance of Q2, because it has negative temperature coefficient. So its resistance will reduce. What will happen then? This Q1 will start drawing more and more current, and as it starts to draw more and more current, then the temperature rises like automatically, because there will be more loss. So temperature will rise and again that resistance will reduce. It will become a cumulative effect, a positive feedback. More the current it will draw, more the temperature will rise, and it will go on drawing more and more current and compared to this device. So after some time, the current will be so large that this device will get damaged. And when this device gets damaged, the whole current will start to flow uh, through this healthy device. And then again, this device is possibly not rated for this much high current as they are in parallel. So ideally, the current should get divided between the two devices. But here, that is not the case. One single device is carrying the whole current. So again, this device will also get damaged. Both the devices will get damaged in this process. So we can't parallel BJT like this due to the reason that BJT has negative temperature coefficient. So that's what I have written here. So the temperature of one BJT increases, the collector emitter resistance of the BJT reduces. The BJT with lower resistance starts drawing more current and incurs more loss, and in turn, the temperature again rises. So, further reduction in resistance, the current difference between the two BJTs increases, and this becomes a positive feedback system, and the devices get damaged in the process, both the devices. Because once one device gets damaged, the other device needs to carry the whole current, so that other device will also get damaged in the process. So, the parallel connection of BJT in this fashion is not possible. It is not a stable system. Okay. So, yeah. Okay for everyone.
Okay, ma'am.
Okay. Even if you don't understand, please tell. Okay. Because I don't know whether you understood it or not. So if you have any doubt, we can repeat any question. You can tell at the end of session also if you have any question regarding any problem or any concept, you can tell. Yeah. So next question is what? Figure shows the connection of two BJTs. Acha, okay. This is the answer. Sorry. Yeah. Here, this is, I think, the easiest question. Two transistors Q1 and Q2 are connected as Darlington pairs. The current gain beta for Q1 and Q2 are given 20 and 25. So what will be the combined current gain? So this is just a multiplication of the two betas. I already told for in Darlington pair we just have a beta which is basically the multiplication of the individual betas. So beta 1, beta 2 should be multiplied. That becomes 500. So you will get a combined beta of 500 while you have the two transistors in Darlington pair. Okay, so this is very straightforward. Next we have this question. In the circuit given below, it is given that beta tends to infinity and VBE is 0.7 volt. Find the value of Vx. So what does it signify? Beta tending to infinity, what does it signify? Can anyone tell? What is the meaning of beta tending to infinity?
Base current is 0.
Yes, right. So beta tending to infinity signifies that beta tending to infinity. For an ideal device, that should be the case. Beta should be infinity. That means we don't need to inject any base current at all. Like for making the device to go in the on condition, there shouldn't be any base current from the source. It shouldn't draw any current from the base source when beta is infinity, right? That is the case here. So we can safely say that IB is here, IB value is 0 here. IB value is 0. IB value is 0 here. So here the current is 0 through this terminal. We need to find the value of Vx. So this is simply the KVL equation here, right? So in this terminal, the source voltage is given 10 volt. Here there is VEE voltage which is given as minus 2 volt, right? And there are two resistances, 5 kilo ohm and 1 kilo ohm. So IB equal to 0 also signifies that my I collector is equal to I emitter, right? Because I emitter is summation of I collector and I base. Here the base current is 0. So I emitter is basically equal to my I collector. So the current flowing here is equal to the current flowing here. This current is 0. Here no current is there. So the current here goes here. So now from now on the concept is simple. We just need to have a KVL equation here. So yeah, so V plus I. First we need to find out what is the current value. So for that we will have KVL here. My VBE is given here. This drop is given as 0.7 volt. At the junction, base emitter junction. So if we just apply KVL here, VBE, then IE times 1 kilo ohm minus 2 is 0. So IE equal to IC becomes 1.3 milliampere. And then if we apply KVL here in this loop, so it becomes minus 10. Like we are just applying KVL. So 5K into IC, then plus Vx plus 1K into IE and minus 2 and again minus 10. So if we solve this, Vx comes out to be 4.2 volt. Is this okay? Have we calculated the value of Vx? Just KVL equation. One in this loop, first in the base emitter loop, then in this loop, collector emitter. So from the two KVL equations, we can find out the value of Vx. Okay. Fine. So yeah, I think there is only one problem after this. Yeah. So capacitive or inductive load when connected to BJT causes abnormal switching transients during. In this slide, I showed you that this slide I showed you. I think that yeah. While explaining the dynamic characteristics, I told that the rise of the current will be linear only for resistive load. But if we have any inductive or capacitive load, this doesn't have to be a linear characteristic. It may be anything, like there may be some overshoot or something. And during this time also, when the transition from on to off is happening, then also the characteristic will be linear only for resistive load. But for any other kind of load, inductive or capacitive load, like this, we can't predict actually, right? That will depend on the value of the inductor or capacitor, how much overshoot we will get. So that's why here the question is given that capacitive or inductive load, what will be the when we will get the switching transients? We will get the transients during rise time and fall time, right? From the picture, it is very evident that during rise time and during fall time, there may be some over transient there. So yeah, so I think all the questions are done. If anybody has any question, you can tell now. Do you have any question in the problem solving section or in the summary section of BJT? Okay, if nobody has any question, what I plan to do was I shall show you one data sheet, right? And in the lecture series, if you have listened to the lectures, so sir has provided like sir has shown you some data sheets and how to see the parameters from an actual data sheet. I will also show a data sheet here, right? So just one second. So can you see the data sheet here? Is the data sheet visible to everyone?
No, actually, the last question is still there.
Okay. Just one sec. Stop sharing. Now is it visible?
Yes.
Okay. So this is the data sheet from onsemi. Onsemi is a manufacturer for semiconductor devices. You will see MOSFETs, not only BJTs, MOSFETs, IGBTs, power modules, everything. If you just visit onsemi, there are some other semiconductor manufacturers as well. Onsemi is one of them. Okay, so you can visit their site and see what are the different types of devices they manufacture. If you look at this data sheet, first there is this number 2N3N03, 2N3903 and 2N3904. This we call the part number. This is called the manufacturer part number. So whenever you need to order some device, you need to give this number. This is the identification of a device. If you give this number, they will understand you require this device, right? So every device has this kind of a part number. Everything, not only semiconductor device, every component. So this is called part number. And here the actual device is shown. Whenever you will see the device, you will not. This is the symbol obviously, but you practically physically if you get the device, it will look something like this. So here it is the numbered. The leads are numbered 1, 2, and 3, and they have given like what are which are which. There are two kinds of packaging. One is like this bent lid, another one is like this. So yeah, this is the and they have given one is emitter, two is base, and three is collector. When you will get the actual device from here, you can identify which terminals are which what. Like so, this is 1, 2, and 3. Then here are the parameters. The maximum rating. First, the maximum ratings are given. So this is the collector emitter voltage, VCEO. This is the maximum value. Okay, this is the maximum 40 volt VDC. Next, there is VCBO. Okay, that is 60 volt VDC. This is collector base voltage. This is collector emitter voltage. Next, we have the collector current, which is 200 milliampere DC, right? So this is the maximum collector current, like continuous current. Continuous current meaning like if there is a continuous DC current flowing through the device when the device is on, This is the maximum current rating, 200 milliampere. And if you see, they have given the dissipation at different ambient temperature, at ambient temperature of 25 degrees Celsius. This is the power dissipation rating, which is 625 milliwatt, right? And D rate above means if the junction temperature goes above 25 degrees Celsius, then you can't you can't just keep on dissipating this much amount of power. You will have to reduce it. Otherwise, the device may get damaged. Derating means you will have to reduce the current so that your power dissipation also reduces as the temperature rises from 25 degrees Celsius. Total device dissipation, and this TC is basically the case temperature. There is one ambient temperature and there is the case temperature. Case temperature means if you see, there is the case. Inside this, there will be the device die and everything that is not visible to us. You will only be able to see the device case, which is the external part. So TC is the case temperature. For this also the device dissipation is given. And operating and storage junction temperature range. So these are the like where what is should be the operating temperature range and the storage junction temperature. These are given. Yeah, and then if you remember for diode we discussed two different resistance, thermal resistances. One is from junction to ambient, another is from junction to case. Junction to ambient is basically the total thermal resistance from the device junction to ambient temperature. That is given as 200 degrees Celsius per watt. And junction to case is given as 83.3 degrees Celsius per watt. So obviously when you will operate the device, you will have to select some heat sink, right? So while selecting the heatsink, you will need this temperature, this thermal resistance, junction to case. And you will have to find what should be the case to ambient temperature so that your junction temperature doesn't exceed this value, this 150 degree, which is the maximum allowable temperature. The junction temperature shouldn't exceed this temperature. And for that, you will have to select heatsink, and the heat sink resistance, thermal resistance should be a value so that the total junction temperature rise should be within 150 degree. Okay, so that's why this data is given here. The process is similar, like the way you calculated for diode. Similarly, you can calculate the junction temperature for transistor. Okay, the same procedure you can apply. And you can also refer to the same equivalent circuit. I think if you remember, I showed one equivalent circuit. So you can refer to the same thermal equivalent circuit. So yeah, this is what. Next we have, there are some other parameters are also there. Collector to emitter breakdown voltage. This is the voltage I was talking about. This is given 40 volt DC. So the device voltage, the device which the device needs to block, it should be within 40 volt, not more than that. Then we have the collector base breakdown voltage also, which is 60 volt. Emitter base breakdown voltage, which is 6 volt. Then base cutoff current, it is given as 50 nanoampere. So below this current, the device will be off. It can't, it will, for the device to be on, the base current should be more than this value. Collector cutoff current is 50 nanoampere as well. And there are for different devices, they have given the IC value for this is on characteristics, right? So from the here you can get the static characteristics of the device. So so here all the parameters are given. You can check it, like you can just check what are the parameters. You can just check online what are the significances of all the parameters given here. So this is small signal characteristics. Then switching character is the rise time, delay time, all the times are given here, right? The fall time, rise time that we already discussed. What is rise time, what is fall time, what is delay time, storage time. All these things are there. Then, and after that, there are some mechanical information as well. Here they have given, and yeah, these characteristics are very important. Okay, so these plots are already, whenever you will calculate loss and everything, so you will have to refer to these plots. This is the reverse bias voltage and capacitance. So this is the junction capacitance, right? So there is a base emitter junction, there is some junction capacitance is present. Okay, so these capacitance values, how they vary with the reverse bias voltage that is given. Then there is collector current and the charge. Okay. Here this is the collector current and this is the charge that it draws. So then there is this collector current and here this is the time. What are the time? The rise time, delay time, fall time, all these times, how they vary with the collector current, it is given here. So all these plots are very important. Okay. So just go through it once. You can see the data sheet of other devices from other manufacturers. You will get similar plots there also. Some small signal characteristics is there that I think we can, for now, we will not discuss the small signal characteristics. But yeah, so see, this is the DC current. I already showed you, right? The beta, how beta varies with collector current. So first it increases, then it decreases. I showed you. So here they have given for 3 different temperatures, -55, 25, and 125. So this is how beta or HFE varies with collector current. Then we have all these collector saturation region characteristics. All these things are given here. Okay. And here the mechanical, the dimension of the device, dimension and mechanical parameters are given here. Okay. So this is a data sheet. I just wanted to give you wanted to show you like what are the different what is there typically in a data sheet. What we can expect from a data sheet of a device. So you can have data sheet, you can see data sheet of a BJT, MOSFET, IGBT, anything, and you will see there will be some data at particular operating points and there will be some curves as we already showed, right? So this data we can refer to whenever we will design a circuit. Okay. So I think for today we can conclude. If anybody have any question, you can tell me. Otherwise, we can conclude today's session. Okay, so I think if you guys don't have any question, I will stop the recording.
Yeah, no question.
Okay, okay. Stop the recording.